This is Tom Sargent, and today I'm going to give you a reader's guide to Chapter 12 of RMT, Fiscal Policies in the Growth Model. What we're going to do is we're going to take the classic Cass-Koopmans, some people call it the Ramsey Optimal Growth Model, and we're going to use that as a benchmark, but we're going to add a government. And we're going to have a government that has to raise some revenues in order to finance an exogenous stream of government expenditures. So we're going to add to the model an exogenous stream of government expenditures, which we're going to fix. And we're going to take it for granted that that's going to be deducted from private uses of resources. And it's exogenous, and the model is not going to explain that. I'm going to put it in a very simple way so it doesn't give anybody any utility. It's quote unquote dropped into the ocean. It's not going to lead to any capital accumulation. And that's done. That's a classic thing that's done in order to simplify the calculations. And you could think of it as introducing a certain kind of separability of utility that comes from public goods versus private goods. Okay, so we're going to say that the government has to finance that, and we're going to follow a paper I like a lot by Robert Hall back in '71, where he did an early version of what we're going to talk about. With a smaller number of taxes than we have. So then what we're going to have is the government has to finance this by issuing certain kind of taxes. And we're going to let it tax virtually everything in sight. It can impose a tax on consumption, a flat rate tax on consumption. It can tax earnings from capital. It can tax earnings from labor. And we're also going to give it, to make life easy on ourselves, we're going to give it a head tax. So if it could impose lump sum taxes. Now we're doing this for a computational convenience, because what we're going to do is we're going to form these taxes as just arbitrary tax rates, and then we're going to compute THT as a residual in order to make life easy for ourselves. So that's kind of where we're going to go. We're going to talk about two kinds of taxes. Distorting tax is a tax rate that has the property that individuals, firms, or households can affect how much taxes that they pay by altering their decision. And that's called a distorting tax. A non-distorting tax is a tax that individuals can't affect the amount that they owe by making some kind of decision. Okay, so what's going to happen is, like, this is key sentence, distorting taxes are going to prevent us from solving competitive equilibrium allocations by solving a planning problem. So we're not going to be able to use lots of the tricks that we used in say Chapter 9 that exploit the welfare theorems. So the allocations that we're going to compute are not going to be Pareto optimal in the sense of Chapter 9. And what that means is we're going to have a different algorithm. And what we're going to use is a shooting algorithm. What we're going to write down is, the strategy is going to be, we're going to write down first order conditions for firms and households. We're going to write down feasibility and government budget constraints. That's going to give us a set of nonlinear equations, actually nonlinear difference equations, and we're going to solve them by using the shooting algorithm. And then we're going to We're going to do some experiments. So that's kind of the agenda, and that's in this chapter. And the role of this chapter is to set up later chapters where we ask, where we do normative analysis. This chapter is all going to be positive. It's going to be in the sense that it's just going to describe that if you impose certain kinds of taxes, this is what's going to happen to equilibrium allocations and prices. It's not going to ask the question, which is the classic optimal taxation question. It's given some government expenditures that you have to finance, what's the best way to do it? That's a great topic, and we're not going to do that here. We're gonna although there'll kind of be some hints that will say, boy, we would really like to do that, but this is just going to be if then. If you impose a certain kind of tax, this is going to be kind of the outcome that you get. So that's where we're going. Okay, so what I want to do is I want to kind of show you how to read this and take you to sensitive things. So here's going to be a thing. We're going to have no uncertainty. There's going to be no uncertainty here. There's going to be a utility function that's going to look like this. There's going to be a representative consumer, or a single household, that gets utility from consuming and from not working. So 1 minus n is not working. N is the amount of labor that's supplied. We're going to assume people have 1 unit of labor each period. So there's some common specifications of utility functions, and we're going to use some of them. Technology is going to look like this. There's going to be a neoclassical production function, f of kn, is going to be linearly homogeneous. And Cass-Koopmans would say that consumption plus investment is less than or equal to output. Capital accumulates according to this law of motion. But what we're going to add is government expenditures. It's going to be non-negative government expenditures that have to be financed. So it's like there's a deduction from output that's exogenous and has a certain pattern. So other than this G, this looks just like a Cass-Koopmans model. Okay, so now, so feasibility, we could write feasibility like this. That's a feasibility. So what we want to now describe is it's a concept called a competitive equilibrium with distorting taxes. So we're going to do this sort of Arrow-Debreu style. We're going to have competitive equilibrium with all trades occurring at time 0. So households are going to own capital. Households are going to make all the decisions about owning capital, investment decisions. They're going to make investment decisions, and they're going to rent capital and labor to a representative production firm. Okay, so the way we're going to do this is, this isn't the only way you could do it, but it's kind of convenient. We're going to define a price system now, and what it's going to be a triple of sequences. There's going to be this Q, where Q we saw from chapter 9. That's the QT. I'm going to omit the 0 here because I'm lazy. QT is the time 0 pre-tax. It's a pre-tax price of 1 unit of investment or consumption at time t. So investment is xt, consumption is ct. Okay. So A to t is the pre-tax price at time t. Look at this, at time t. The timing matters. That the household receives the firm for renting capital. It's a rental rate of capital. And WT is, again, the pre-tax price. Those are pre-tax prices. Those are the things to focus on there. So those prices are, so notice this, I've scaled the prices in certain ways to make budget constraints easy. So all we're going to do is going to do this in the time zero, chapter 9, error de Brue context, where we're going to have taxes. So we're going to say that government, we're going to have to talk about a government budget constraint. So we're going to have a government expenditure and tax plan that satisfies a budget constraint. We're going to call that budget feasible. Budget feasible. So what's going to happen is there's certainly not going to be a unique competitive equilibrium, even with a GT sequence that's given. There's going to be a manifold, a manifold of competitive equilibria that are going to be indexed by government tax policies. Okay, so that's a key thing. So we're going to be in the business of characterizing this manifold, and to do that we're going to have to dip down and put some restrictions on some of the tax sequences, and then see what the consequences are. That's the whole structure of this chapter. So the government faces at time zero, this is a time zero budget constraint, this thing done error de Brue style at time zero. So what the budget constraint, well, the household faces a budget constraint like this. It's going to pay a tax on consumption. So that's a flat rate tax on consumption. And so we have to, it's not just Q times C, it's now Q times 1 plus tau C. That's what it costs for consumption, because you've got to pay the tax. We're not going to tax investment when you make it. We're going to tax the returns on capital. And then, so this is the present value of, the left-hand side of this is the present value of the household's purchases of consumption and investment goods. And the right-hand side, that's the present value of its rentals from capital minus the tax rate. So you could read about this. We're gonna have a depreciation allowance for capital. So that's the tax it pays on earnings of capital. It gets wages here, but it pays a flat rate tax on labor, and then it pays this lump sum tax. So these taxes are distorting because they multiply decisions that the household has an effect on. And then the government faces this budget constraint. The present value of government expenditures is less than or equal to the present value of its tax revenues. So it taxes consumption, it taxes rental rates on capital after a depreciation allowance, and it taxes labor, and then it has a head tax. So we've given the government a whole bunch of kinds of taxes, and there's a couple senses in which we've given it too many. We did it on purpose so that we can understand the consequences of different taxes. That's the whole deal here. Okay, so that's a budget constraint. Okay, I want to take a little digression here, because embedded in this setting is, as usual, as we saw with error de Brue in chapter 9, there's a whole theory of the term structure of interest rates, and that's what this little section does. It just writes Q, just rewrites Q using this equation and then reinterprets it. And we regard this thing as a so-called one-period discount factor. And then we can get a whole theory of the a whole theory of the term structure of interest rates is embedded in these Qs. So this whole Q sequence, that once we know that, we know the whole term structure of interest rates, and we can use these formulas. So this section reviews this, and it gives you this nifty formula. It's a classic formula. J.R. Hicks, I got a version of this formula in his book Value and Capital, and that ignited the whole modern theory of the term structure of interest rates. It's based on this equation, and we're going to come back to this in a little bit. Well, a key thing, actually, if you read this, if you're interested in the term structure, you read this, you'll see a sharp characterization of this formula, and where it comes from is that is right here. It's the equating of the gross rate of return on any asset. The one period return has to be equal for all assets because there's no risk. And that's what's embedded in here. So I'll let you read that quickly. So let's see, we do this. And then here's something in the spirit of chapter 9 that I urge you to look at. What we're doing here is I'm just kind of giving you a reader's guide, and chapter 12 should be easy to read if you've mastered chapter 9, because we're going to kind of go through steps. What we're going to do is we're going to take the Arrow-Debreu version of the government budget constraint, and we're going to rewrite it taking Arrow's view and write it in terms of one period Arrow securities and get a sequential version of it. Because why? Well, that's often done. Lots of times people will write down one. They'll often write down the Arrow version and not the Arrow-Debreu version. But it's good to know both. So so that's what's done here. It's just to conserve notation. We time T tax revenues. That's what we're given by this formula here. It's given by that is you tax consumption, tax capital, tax labor, and you have this head tax. Just call that TT. And now the government budget constraint is just this. It's the present value of government. That's the Arrow-Debreu version. And now what we're going to do is we're just going to use it's kind of the logic of dynamic programming. We're going to break the sum into a today and a tomorrow. And then we're going to stare at it and do a little math, and then what's going to happen is we're going to get a time zero. We're going to get a sequence of budget constraints that looks like this. That what this says is government expenditures today is equal to government expenditures today plus the amount of debt that you rolled over from last period, and that's due. That has to be covered by today's taxes and new debt that you issued today. That's what that equation says. Well, that's embedded in this with an appropriate definition of BT. And what is BT? This is beautiful. Government debt is just defined here as the present value of future surpluses. This is a key equation, which what it says is high government debt today signals that in present value there's going to be surpluses tomorrow. That's the theory of government debt that's embedded into this. Okay, so there's some more arithmetic here, and this is useful because people like the Fed and the IMF and the Treasury, live with these equations each day and do accounting based on them. Okay. Well, another thing we did in chapter 9, and we also did it in a couple thing when we did the Basine Clementi-Gotardi model. We had a Modigliani-Miller theorem, and we also had an irrelevance theorem when we talked about essentially the real bills doctrine when we were studying overlapping generations. Well, it turns out the maturity structure of government debt is irrelevant. Whether the government debt issues long or short, or when it's due, it's irrelevant. And there's a version of that in this, and it's pretty easy to do. So that's what's done in this little section. The logic's kind of the same. The logic goes like this. Logic goes like this. It's fundamentally, if you come back here, what it says is the government has to finance, in terms of error to boot prices, it has to raise revenues that in present value equal the present value of government expenditures. It has to raise at least that much revenues. And how can it do it? Well, it can time its taxes difference. It can tax now or later. And this budget constraint doesn't care. You could set all these things, you could set tau t equal to 0 for t equals 0 through some big number cap s, and then after that do all your taxing. And if you do that, what you would be doing in this other notation is you would be financing today's government expenditures by issuing debt, and it would be piling up. It would be growing, but it couldn't grow forever because it would have to satisfy this equation. That's kind of the logic behind the irrelevance. So as long as that budget constraint's satisfied, it doesn't matter. So it's irrelevant for the that budget constraint. Okay. So what we're going to do now is define a competitive equilibrium with distorting taxes. And you could figure this out because we have to just make a list of things. The representative household is going to choose these sequences, and it's going to choose those to maximize the utility function I told you. Representative firm is going to choose capital and labor to maximize the present value. Look at this. This is the present value of profits. That's output minus the rental rate on capital minus the rental rate on labor. So that's what the firm does. Both the firm and the household are price takers. And then the final thing we need is we have to have a budget feasible fiscal policy. So stare at this definition: a competitive equilibrium of distorting taxes. It's a budget feasible government policy. It's a feasible allocation and a price system for which, given the price system and the government policy. See, we didn't have to do that in chapter 9 because there was no government, but now there is. So given the price system and the government policy, which includes tax rates that the people take as given, the allocation solves the household's problem and the firm's problem. And of course, I said the policy conforms to the budget constraint. Okay. So what do we want to do next? Well, we want as I announced in the beginning, we want to write down a set of equations. They're going to be nonlinear difference equations ultimately, whose solution is a competitive equilibrium with distorting taxes. So we're going to get prices and an allocation. So to do this, what we can do is we can use a trick that we've used before. This is used over and over again in general equilibrium theory and in finance and asset pricing theory. We're gonna get no arbitrage pricing formulas. So those are going to be no arbitrage pricing formulas. So what we're going to do, so how did we do that before? We took the household's budget constraint and we kind of rearranged it. So if you do that, you can get the household's budget constraint and kind of use the law of motion of capital. And if you get it, you could do the work, you rearrange it into this. And then if you notice this is the interesting term is on capital. And if you do this, it's got to be true. It's if this object were not zero, there would be an arbitrage, meaning you could raise the right-hand side of the budget constraint to plus infinity. But that couldn't be possible in an equilibrium, so then you conclude that therefore this has to equal zero, that thing in zero. And that gives you a restriction. That gives you a restriction on equilibrium prices and quantities. So that's what we do. And so that's explained here. That's explained here. It's a nice argument. And what it leads to, once you do it, it leads to this nice formula. That's a nice formula for that involves the tax rate, the Q's, and the rental rate on capital. And this formula was derived in some famous work by Robert Hall and Dale Jorgensen to lead to something called the user price of capital. We do some other logic, and we get this from using that same equation. We get this terminal condition. So we get a few equations, and if we use this again, I'm just kind of telling you how to read this. If you use this equation and rearrange it, you get this famous equation from Hall Jorgensen. It's called the user cost of capital formula. Okay, that's where that came from. So, on first reading, so there's these formulas that are kind of classic. Hall wrote that other paper, which I really like, around, within a few years of when he derived this formula for with Dale Jorgensen. And then, actually, the way to read it is Hall derived this formula with Dale Jorgensen, and then he kind of put it to work in the context of a version of the model we're talking about now. Okay, so now what we do is we get our household first order conditions. And I'm going to assume, so we get our household first order conditions. So we get this condition for consumption, this condition for employment. And then here's another digression on the term structure. Once we knew the Q's, we get a whole theory of term structure, and we know something about the Q's from here now, from this marginal condition for the household. So that tells us something about how taxes are going to affect the term structure, because this is a nifty equation that restricts the relationship between the Q's, consumption, and consumption taxes. So consumption taxes are going to affect the term structure. That's what this tells us. Okay. For firms, well, we're going to get kind of standard logic is we're going to get competitive equilibrium conditions that the rental rate on capital is going to have to equal a marginal product of capital, and the rental rate on labor is going to have to equal marginal product of labor. Okay, so pause for a minute, catch our breath, and now say we're going to have to compute a competitive equilibrium with distorting taxes, and how are we going to do it? Well, what we're going to do is we're going to form a system of difference equations, and we're going to attack it. So this kind of tells you the setup. Okay. Now what I'm going to do is I'm going to assume at the beginning, at first, just to get started. Later in the chapter, we'll relax this. We'll assume that people don't get any utility from leisure. So they're going to work all the time. And so our utility functional is just going to become this. And then we're also going to express so there's one representative person who's working 1 unit each time. It's kind of convenient to express output per capita. So F of little k is output per capital. And we can write the feasibility condition like this. This is going to be one of our equations. And then we can write the if we take this equation and substitute it into the household's Euler equation for consumption, we'll get this equation, which we can write like this. So what we're doing is we're boiling down the marginal conditions from the firm's problem and the household's problem into a difference equation, a system of difference equations. And this is going to be, so this feasibility condition is going to be one of them that you're going to see. That involves consumption and capital, given government expenditures. And this involves consumption at different dates. It's got an Euler equation. It involves taxes at different dates, a tax on capital, and involves this. This came from the rental rate on capital, the marginal product of capital minus delta. So this is one of the equations that we're going to want to solve. And these are equations purely in allocations and government expenditures and taxes. We have eliminated prices by using the marginal conditions. Okay, that's what we said. So we've got ourselves down to these equations. Okay. So this equation and this equation are going to kind of be key to us. Okay. So what we're going to do is we're going to solve this using the shooting algorithm. So I'm assuming you've seen that, so I'm going to go over it quickly. Again, you can see it from the Cass Coupons lecture in QuantEcon. So to use the shooting algorithm, we have to have something we're going to shoot for, and what we're going to shoot for is a steady state. So we're going to rig things so that a steady state exists because we're going to assume it exists. So what we're going to do to get a shooting algorithm, well, the first thing to note is I'm going to proceed formally. I'm going to take these equations and I'm going to rewrite them. It's kind of a generic, this is what's going on here, as generic difference equations. So I'm going to define ZT. ZT means forcing functions. So I'm going to have government expenditures, tax on capital, and tax on consumption. I'm going to have them be my forcing variables, stack them into a vector Z, and then I'm going to write those key equations that I had above, those two equations, as this system of difference equations. It's a system of difference equations in capital. Actually, should be this one. Should be this one, because I've substituted out consumption. So yeah. Okay, good. Let's just proceed. I'm going to write this as this system of equations. And what I'm going to do is I'm going to assume that government policies have the property that they eventually settle down to a constant. And I'm going to define a stationary point. Notice that this is a second order difference equation in KT. That's what this is. That's what that is. So I'm going to write that equation because look, it's got KT plus 2, it's got KT plus 1, and it's got KT. And it's got the G's are driving it. And it's got a tax sequence here, tax sequence here, tax sequence here. That's how this equation took this form. So I'm going to assume that government expenditures and taxes eventually settle down. And now I want to compute a steady state. So it sounds hard, but it's actually quite easy. Because if you stare at it, you can actually solve this equation by hand, and it gives rise to something classic. In a steady state, this equation has to be true. 1 is equal to beta times 1 minus the steady state value of capital tax times this equation. If we let beta equal 1 plus rho, and we rearranged, we get this equation. So this is an equation that gives us, we can solve this equation for K bar, the steady state capital stock, as a value of the steady state capital stock as a function of only a few parameters: delta, the depreciation rate; rho, the discount rate; and the tax on capital. And when the tax on capital is 0, you get this formula, which is a famous formula. It's a formula for the Cass-Koopmans augmented golden rule. So that's the optimal stationary capital stock that solves this for an economy without a government. So if you could read this, that's how we're going to compute the steady state that we're going to use for the shooting algorithm. So now, kind of, we're all set up to to actually apply the shooting algorithm. And I'll just conclude this little lecture by telling you what the steps are. So what the shooting algorithm is going to go like this. We're going to have an economy where eventually government policies are set such that a steady state exists, and we can be confident that we'll converge to it. Now, that's a consequence of our making assumptions about government expenditure and tax policies. We're going to do that. So then the algorithm goes like this. This is going to remind you of the step one is we're going to solve for a steady state. That's easy, capital. Then we're going to select a very large time index S at which we have definitely converged to a steady state. And then what we're going to do is we're going to guess. Key thing is we're going to guess at an initial consumption rate C0. So there's good and bad ways to make a guess. I'll show you a good way later. So we're going to guess at C0. And then once we know C0, we can compute U prime of C0, and then we can solve this equation for K1. And then we can solve, once we know K1, we can solve for U prime of C1. But if we know U prime of C1, we can compute C1. So then we're going to compute K2, and we're going to iterate all the way out to S. And now we're going to check to see whether the capital that we got from doing this is actually equal to the target that we're shooting for, K bar, the steady state. If it isn't, if it is, we're going to quit. We're done. We made a great guess. If it isn't, we're going to go back and change our guess for C0 and do it again. And then what we're going to do is we would have computed all the prices and allocations, and then the final thing we're going to do is we're going to compute the present value of the head tax that we need to do in order to satisfy the budget constraint. So this is a residual. So I can tell you how good theses are written. There's a prominent economist at the University of Minnesota now, Ellen McGrattan, and what she did is she looked at a model like this, and she saw this head tax, and she said, that's not realistic to head tax. I want to construct a model where there's no head tax, but there are distorting taxes. And what she did with her thesis years ago was she put, I'm going to insist that I'm going to put another loop here, and I'm going to insist that the head tax have the property that it's zero always. So you can't do this. And now what I'm going to have to do is I'm going to have you adjust one of the other taxes, either a tax on capital or a tax on consumption, to make sure that the government budget is balanced. So she did that, and around the same time another economist, Tony Braun, did that, and they got some very important papers from doing that. Okay, what we are not going to follow her route. We're going to, for ease, we're going to let the present value of the head tax be a residual. So we'll stop here for now, give you time to digest this, and then we'll actually put it to work, and we'll compute what the rest of this chapter is going to do, and I'll take this up in the next little lecture, guide you through and show you some of the consequences of imposing different kinds of taxes.